I'd like to talk about a laboratory we've been putting together up at Lawrence Berkeley called the Demand to Grid Laboratory. And this is a laboratory that's dedicated to demonstrating and understanding demand response capabilities, particularly in devices that reach further out into the distribution grid, in particular residential environments. So a little bit of background. Some of the areas that we're interested in performing demonstrations and testing on, how well we've worked our way through that list to date. We just finished laboratory implementation probably about 6 to 8 months ago, and now we're starting to work our way through some of the first preliminary results, which I'll get into later. Key lessons that we've learned, and also a little bit about future demonstrations. So this is all about demand response, which we consider to be the ability to remotely reach out to active loads and request moderation or reduction of loads based on system-level concerns. And so we've been involved in this area for quite some time, and back in 2002, for example, we started working on the development of an internet application-level protocol called OpenADR, Open Automated Demand Response, that was essentially an attempt to codify the particular data structures that are needed to communicate to loads and indicate what sort of demand reduction was being asked for and what kind of demand reduction was being responded to. So we've looked at the low-level communications issues. We've looked at some of the control algorithm strategies that you would like to have at either at the location of the device whose demand is being modulated, or at the larger institution, say the building level, that's being responsive. And we've looked at how these can be rolled up into building environments where you'd like to understand what the response of a building would be, for example, to a demand response call. And we've also looked, in fact, we've spent most of our time looking in the industrial and agricultural area. For example, asking questions like, does it make sense for a refrigerated warehouse to be demand responsive? And turns out in some cases they can be. If you look at agricultural applications, is there a reason to try to make agricultural water pumping demand responsive? Well, the answer is yes, and we have some results there as well. But what in this particular environment, what we'd like to do is to understand how this pushes its way further down into the distribution system, in particular into the residential and small commercial world. So what has really given this whole area a push is obviously the smart grid. The availability of communication paths alongside of power distribution paths means that there is the potential and therefore the promise to make loads more responsive because they will have communication paths that between generation and consumption. And so over the last year and a half, we've been working on this. We obtained seed funding from CEC, and I'd like to tell you what we've managed to achieve. Immediate goals, we'd like to look at some of the base technologies, obviously the communications technologies, of which there are several that are getting a lot of attention by both vendors and utilities. We'd like to also evaluate and to work with vendors to better understand the particular strategies that appliances and other subsystems use to respond to demand reduction requests, events. To see how this might be folded up into an integrated view of building performance, which, as we all know, is a critical benchmark for how one implements demand response and measures its effectiveness, and also to take some of the tools that we develop and feed them back into building simulations. And lastly, we're just beginning to look at some of the security, cybersecurity in particular, issues and some of the privacy issues that come along with this increased communication between utilities and aggregators and end users. And we're just starting to work on that area. So the four key demonstration areas that we want to focus on: residential appliances and the home area networks on which they communicate. This includes also communications between appliances and the residential smart meter. We'd like to look at OpenADR, or basically networked demand response technologies, understand some of the systems issues and particular end-use requirements. We specifically also want to look at lighting systems, their controllers and their system-level implementations. And then finally, to get some grasp on the kind of data analytics and displays and visualization that vendors and utilities have been putting together to drive these applications. I won't talk about it here, but we're also actively working on EV charging systems. Everyone has an architectural drawing. So this is supply versus demand separated vertically, and in between are the communications paths that are used to transfer messages across them. Primarily, it's the secure internet, hopefully using secure protocols, and or the AMI network that utilities use to communicate between their facilities and meters and ultimately into the home. But it's been clear to us from the outset, and now that these issues are being approached in a more systematic and rigorous way, it's been clear to us that there's another part of this picture that will require attention, and that is the information infrastructure on which these messages and their semantics will be played out. And so we've started to try to formalize the pictures of what the various components are in this information field and how they are supposed to interact with one another, and therefore come up with some beginning of an understanding of what the interoperabilities will be at the information exchange level as opposed to just the communications level. So who are we working with? Well, we're working with a number of vendors who have been very good about lending us devices for evaluation and to some extent testing. General Electric for a number of appliances, CloudBeam, Nest. We also have two smart meters from two vendors, Itron and Silver Spring. We're working with AutoGrid and Akuacom in the open ADR implementation world, as well as several lighting companies. So, down to the, let's get real, as they say. So we have multiple implementations of all the devices you see on the right. And this particular residential appliance and hand integration topic is looking at, obviously, devices in the residential area. One of the things that was clear to us is that in this area, there's a tension between two communication patterns that seem to have gained foothold in the marketplace. One is the ability of utilities or aggregators or service providers to reach directly into the home through their IP, their internet gateway, and to talk directly to appliances or to platforms, residential-wide platforms such as the GE Nucleus, to express some kind of energy policy or exchange or archive information about energy usage within the home. The other pattern is that which takes place between appliances and the local smart meter, which the smart meter acts as a proxy to information that is provided to it over the AMI network from the utility environment. We see these two communications patterns kind of fighting it out in the marketplace, and in some instances we've seen vendors who have embraced both of them and are still struggling to try to figure out what functions live on which side of this, in which of these two patterns. So what are the DR strategies that we see in the appliance world? Well, things like delayed starts for things like washers and dryers. It turns out this is a very sensitive topic for appliance manufacturers because they want to maintain control over when and the various modalities in which demand response takes place in those environments. It can't simply be an interruption of service, for example. The obvious example is a bleach cycle, which could stop mid-cycle, is definitely not something that a washer manufacturer would like to have take place in their equipment. Delayed onset of defrost cycles in refrigerators. Even in the case of electric ovens, reduced temperature set points, which has obvious implications for cooking patterns. But a lot of this discussion is still going on, and very much what we have discovered so far, part of active development in the appliance world. What's interesting, though, is that as end users and as researchers, a lot of these strategies are still very opaque to us. They're not in the manuals. They're typically not known to the people who are selling these devices. And in fact, we've had to be a little creative in trying to understand just what strategies are behind our demand response requests. So this is a slightly different picture of that environment, tabular form. And the granularity that we're seeing here in terms of the appliance world is fairly coarse, low, medium, high, and critical. But what's interesting is that even in this environment, some of the lower, the less important demand response events don't take price power costs into consideration. Now, that's fine, but an understanding of what that is and how it might be folded into models for, say, larger ensembles like a subdivision or those homes that are within a particular substation's service area, that would be very interesting for us to understand so we can fold it into larger scale simulations. Second area, open ADR. So we've looked very closely at the kinds of new devices that are showing up in this world. So demand response, at least in the far past of maybe 10 years ago, was focused on fairly large buildings and installations where one could have a single point of contact and have a policy respond to a particular request from a utility or a service provider. What we've seen is that technology has caught up with this environment, and we're seeing open ADR and other demand response communications protocols push down into smaller and smaller devices. We've seen them show up in plug load controllers. We've seen them show up in thermostats. And we expect to see them show up in a number of other areas. And so we see communicating thermostats, for example, that can be directly responsive to open ADR requests. And we're trying to understand just what the impact of having an independent path into the home for demand response might be and how the home can coordinate its responses to these requests. Which leads me to the next topic, which is LED lighting. So LED lighting has obvious benefits in the home in terms of energy efficiency. It is by far the most efficient of the commercially viable lighting technologies that are out there. But it also tends to be one of the most controllable. And what we're beginning to see are open ADR technologies and demand response technologies that interface directly to lighting fixtures. And so, for example, in the D2G lab, we have both these large fluorescent light ceiling fixture replacements and simple T8 fluorescent light fixture replacements that are interfaced directly to open ADR devices. And so we've seen some interesting results as to how one might be able to both not just reduce lighting when possible, but in fact lower lighting levels for extended periods of time with having relatively little impact on occupants of that particular room. And in the last of the four areas, I'd like to point out that each of these vendors in each of these areas have all been very creative in trying to take their control environment and their data environment and present that to the user in interesting ways which will capture their attention and hopefully increase their interest in reducing energy consumption in their home. So, for example, this is a visualization page from the GE Nucleus system, which we have installed in the D2G lab. And you see a little bit of everything up here. You see instantaneous usage. You see a pie chart of subsystem comparisons within the home, those that this particular system knows about. You see a little bit of pricing information. You see historical information. But the interesting thing is that at no place in this system can you get a picture that looks like that. Some vendors simply have not decided to or understand the importance of making simple, raw data available to other applications, analytics, or perhaps other display modalities. So, for example, this is a power display for a 24-hour period for the washer in one of our appliance tests. And this is the refrigerator. You can get information like this by looking at the web page and scraping the HTML. but in the process you lose all the semantics of what the information means, what its measurements what the metadata is for the measurements. All of that kind of disappears because you're not quite sure what you're looking at. So again, we think that as interesting kind of middleware analytics become applications become valuable and useful, we're going to see more and more usage for this machine-to-machine communication, and hopefully vendors will be more responsive to the needs for conveying raw data between applications. So this kind of leads me to preliminary conclusions. So one thing that I've got to stress, and that is at the present stage of development, just demonstrating that this equipment can be deployed and run and have its reliable operation observed is extremely, extremely important. Even at this seemingly late stage of development in terms of appliances and other subsystems, we saw networking issues show up simply because manufacturing development was done in an environment where they thought they were in a subdivision with homes with a single wireless network available or visible from a particular appliance. In a research lab or a commercial environment or even a large apartment building, you see multiple networks in that environment, and it caused problems with at least one of the devices that we tested. And so just literally plugging them in and making them work is of high value. I mentioned that the response of each of these devices to DR requests is still somewhat obscure, and it makes it difficult for consumers and definitely for researchers to understand exactly what kind of strategies make sense and how to incorporate those strategies into simulation efforts so we can talk about the kind of large-scale impact of demand response. So we'd like to see that clarified a bit. And at least at the moment, regardless of the commitment and success in complying to communication standards and data representation standards, most of these systems still live as independent siloed applications. And we think for this marketplace to grow and to be truly useful, there's going to have to be better interoperability between components. Something else that I haven't really talked about, but if you look at a residential environment and want to simulate that environment and include the connection to the utility through the smart meter, that becomes a very expensive and very difficult environment to properly simulate. And part of that is simply because metering systems are proprietary and complex, and utility operating systems are equally as complex and proprietary. And it just becomes too large a task to bring that environment, to simulate that environment in a relatively small laboratory setting. And this will point out to, I'll cover this on the next slide as well. And so that's just something to be aware of, how the degree to which you'll be able to simulate in full fidelity this environment. And also, we're going to have to come to terms with data access, even within the home, putting aside issues of privacy. Just what data will you be able to get access to, or what data an application on your behalf will be able to get access to from these devices. So path forward. We really strongly believed, and it was certainly reinforced by our experience so far in the D2G lab, that we really need a standardized open residential energy gateway. And by that we mean a platform, a computing platform, an inexpensive computing platform that provides a single point of contact to convey utility and or metering information into the home environment, and a single platform, the same platform, that would act as a single point of contact for appliances within the building to have access to unified demand response requests, and as well as getting access to that very same utility and smart metering data. Many people have echoed this sentiment, and a number of projects have been started. The particular one that we've been working on, and we'll be working on a bit more in the near future, is one we call the Open Smart Energy Gateway, or OpenSeg. And in talking with other folks here, both on campus and in other institutions, there are many similarities that cut across this desire. So another picture, we've been working with some folks at Rainforest. They have a device that comes very close to what I've just described, but it doesn't quite fulfill the requirement that we would like to see, for example, of having a device that represents not only a ubiquitous access point whereby a home appliance or home computer or home tablet can get access to utility green button data, but also be able to take information from the house's actual operating environment and present that into the home in a similarly formatted pattern as well. Future, we all want to have a future, and so we're going to be looking at extending our OpenADR work to include the newest version of OpenADR, which hopefully will be complete the standardization process soon, which is OpenADR 2.0. Also looking for further auto demand response demonstrations and facilitate relevant research work. And that's all.
We can take one burning question and we'll have a break. Like Chris has a burning question.
If I understand you right, it sounds like the manufacturers of appliances are kind of winging it on how this equipment responds to demand response requests. And I was just curious, hasn't some reference specification or guidance been developed through the smart grid processes that have been led by NIST?
Well, I've heard several renditions of that. I know that I think for very obvious reasons, the appliance manufacturers very much want to be responsive to their customers, and so they're caught in this bind where they would like to demonstrate that they have that they can allow their customers to save money, but they would also like to perhaps minimize the inconvenience that their customers might see in terms of having altered operational patterns. There's been a lot of standardization in terms of how one might be able to convey attempts at standardization, how one could convey demand response requests to a device. But the actual behavior of that device in response isn't really mandated by smart grid standards, and in all practicality probably shouldn't be. But there's still a lot of toing and froing, so to speak, going on in trying to understand just what you would like a refrigerator, for example, to do if you were in a critical demand period. And they're still working it out. That's...
Thanks so much. Let's take a 10-minute break.
Thank you.